In this video, we will state and prove the replacement theorem. It's a long and involved proof. I've drawn a picture here to try to help you understand what these sets are that we'll be talking about. V is a vector space, and G is a finite set. It has n elements in it, n vectors, and it generates V. So it might be much bigger than a basis, but it's a generating set for V. L is a set with m vectors in it, and L is linearly independent. So the theorem tells us that given this situation, that m is less than or equal to n, right here. M is less than or equal to n, and there exists a subset H of G that I have in red there, containing exactly n minus m elements that we could move from G to L, and then the set L union H now has n elements in it, and it generates or spans V. So we have a linearly independent set, a generating set. The number of elements in the linearly independent set will be less than or equal to the number of elements in the generating set, and in fact, if it is less than, we can move n minus m elements vectors over to L and increase L to be a generating set. In neither case, G nor L union H is claimed to be a basis. The proof is done by induction on M, the size of L. So we start with our base case, and we will say if M is equal to 0, well then L is empty. So we can move over all of G, n elements over there, and we would have L union G generates V. L union G is just G. So G does the job of H. So it is true when M equals 0. Now we'll make our induction hypothesis. Suppose let's call it RT, the replacement theorem, is true for L, a set of m linearly independent vectors. In other words, m is less than or equal to n, and there is a set H that we could adjoin to L and get a generating set. In other words, L union H spans the vector space, where H is a set of n minus m vectors from G. So now I want to show that the theorem is true for m plus 1 vectors in L. So we'll let L be equal to m plus 1 linearly independent vectors, v1, v2, v sub m, and v sub m plus 1. Let L be that set where the v sub i's are linearly independent. Well, then, if we take one of them out, namely v sub m plus 1, we have a set of m linearly independent vectors, v1 through vm. This is linearly independent, and so by our induction hypothesis, I'll just put HYP, we know there is a set, and let's call it, how about U1, U2, through U sub n minus m. There are exactly n minus m vectors. These vectors are from G, such that if we adjoin them to the V sub m's, we get a generating set. So let's write down what that set is. V1 through V sub m, and putting in U1 up to U sub n minus m, we have exactly n vectors there, and this set generates G. We're also given by our induction hypothesis that m is less than or equal to n. But I'd like to argue right now that we can do better than that. In fact, m is strictly less than n, and we need that. So see why. If we didn't need any elements from H to bring this up to a spanning set, then that would contradict the fact that V sub m plus 1 cannot be written as a linear combination of the V sub i's from I equals 1 to m. So m is strictly less than n. So that last line was that we have this generating set for G. Well, remember, we had removed V sub m plus 1 in order to use our induction hypothesis. So now that we have a generating set, I could say, well then, V sub m plus 1 is equal to A1 V1 plus up to A sub m V sub m plus, how about B1 U1 plus up to B sub n minus m U sub n minus m, because it was a spanning set. So we need to point out that at least one of the B sub i's is not 0. And without any lack of generality, we can assume that this B1 is not 0. Now, why can we do that? Because we know that V sub m plus 1 is linearly independent in L. And so if all of the BI's were 0, then we would have V sub m plus 1 written as a linear combination of the vectors V1 through Vm, which is impossible. So we know that at least one V sub I is not 0, and we're going to assume that it is B1 without any lack of generality. Okay, so I could, at this point then, solve for U1. And so I'll put this on pause and write it out. Okay, so I solved for U1. I moved B1, U1, I moved everything else over, except for B1, U1, and then I divided by B1, which we agreed was not 0. Notice that I have brought back in V sub m plus 1. We have now expressed U1 as a linear combination of all of the V sub i's and the rest of the U sub i's, not including U1. So now I would like to just claim that H, the set that we're going to put in with L up here, H will be everything except for U sub 1. It'll be U2, U3, up to U sub n minus m, coming from G. That will be my H, and I will now prove that L union H is a generating set for V. If you're taking notes, you might put it on pause right now and finish your notes, because I'm going to erase again. This was the generating set that we had, and now we have expressed U1 as a linear combination of the VI's and UI's, including V sub m plus 1. So all I'm going to do here essentially is just take out the U1 and replace it with V sub m plus 1. That's what we just proved we could do. And this set is L union H. So L union H generates G. We needed that. And L union H has exactly n vectors. And that's easy to see. We have m plus 1 of the v sub i's, and we want to add to that n minus m minus 1 because we took out u1, and that's equal to, of course, m. So it has exactly n vectors. Oh, and remember we said it was important to remember that m was less than n, so m plus 1, that's the number of vectors in L, is less than or equal to m. So we have this done. We have the subset H of G containing exactly the right number of vectors, and L union H generating V. Therefore, the replacement theorem is proved by induction.